There is a place where the universe ends. This is not science fiction, but the stark prediction of our best science. At the edge of a black hole lies the event horizon, a boundary so absolute that crossing it means leaving our reality behind forever. By the end of this exploration, you will understand the competing theories that physicists use to describe the indescribable, from the crushing of stars to the birth of new cosmos. We will confront the paradox of information vanishing into darkness and the tantalizing hints of gateways to other worlds. What do you believe lies in the ultimate heart of darkness? Think of the universe as a river flowing over a waterfall. From a distance, you see the water moving smoothly, but as it nears the edge, it accelerates, curves, and then vanishes into the mist below. The event horizon of a black hole is that precise lip of the cosmic waterfall. It is the point of no return, the final boundary where the river of spacetime itself plunges out of sight, taking light and information with it forever. This is not a solid wall you could touch, but a mathematical line drawn in the fabric of reality. It is defined by what scientists call the Schwarzschild radius, a distance from the black hole's center where the pull of gravity becomes so intense that the escape velocity equals the speed of light. Nothing, not even light, can climb back out. As the renowned physicist Kip Thorne described it, the event horizon is a one-way membrane. Things can fall in, but nothing, absolutely nothing, can come back out. This creates one of the most mind-bending effects in all of physics, a phenomenon called gravitational time dilation. Imagine watching a friend, brave or perhaps foolish, falling toward a black hole. From your safe vantage point far away, you would see something strange happen. As your friend gets closer to that invisible boundary, their clock would appear to tick slower and slower compared to yours. Their descent would seem to stretch out, their image reddening and dimming. At the very moment they reach the event horizon, from your perspective, time for them would appear to stop completely. They would be frozen there, a ghostly silhouette etched onto the edge of forever, never quite crossing from your point of view. It is a cosmic illusion born from the extreme warping of spacetime. For your friend, of course, their own clock ticks normally. They would cross the boundary in a finite moment, passing from our universe into the unknown without any dramatic local sensation. This is the central paradox. The event horizon is both a real boundary for those who cross it and an eternal, unattainable mirage for those who watch from safety. If our vision and our physics seem to break down at this edge, if reality itself presents two contradictory stories, how can we ever hope to know what lies beyond? To answer that, we must move beyond observation and into the realm of pure, powerful theory. But for the astronaut who crosses that horizon, the story does not end with a quiet passage. From their own perspective, the journey inward is far from serene. As they fall deeper, a strange and violent transformation begins. If the black hole is of a certain size, the difference in gravitational pull between their head and their feet becomes unimaginably strong. This is the tidal force, the same cosmic stretch that the moon uses to create ocean tides, but amplified to a horrific extreme. The force at their feet, being slightly closer to the black hole's heart, pulls far harder than the force at their head. The astronaut is stretched, elongated, pulled into a long, thin strand of atoms. Physicists call this process, with grimly accurate poetry, spaghettification. It is the physical signature of a space so warped that it treats a human body not as a single object, but as a collection of particles on individual, doomed trajectories. This is the fate predicted by Einstein's theory of general relativity for anything venturing too close to a stellar mass black hole. For a supermassive black hole, like the one at our galaxy's center, the event horizon is so far out that the tidal forces there are gentler. You could cross it without immediately being shredded, buying you a little more time before the inevitable pull takes hold. But according to relativity, that inevitable pull has only one destination. All paths inside the event horizon, every possible direction, point toward the center. There is no orbit, no sideways movement, no escape. Space itself flows inward faster than light can travel outward, like a river current too strong to swim against. All matter that crosses the horizon is funneled, compressed, and dragged relentlessly toward a single point at the very core. This is the singularity. In the equations of general relativity, it is a point of infinite density, where all the mass of the black hole is crushed into zero volume. Here, the curvature of spacetime becomes infinite. Our reliable map of the universe, the mathematics that describes planets, stars, and galaxies with stunning accuracy, simply breaks. The equations spit out nonsensical infinities, a clear sign that our understanding of physics has reached its limit. It is like using a standard map that shows longitude lines converging at the North Pole. The pole itself isn't a physical tear in the Earth. It is just a place where our particular coordinate system fails, a coordinate singularity. But the singularity at a black hole's heart is predicted to be different, a true physical singularity where the laws of nature as we know them cease to function. What does infinite density even mean? It suggests a place where matter is compressed beyond atoms, beyond nuclei, beyond any conceivable form. It is a boundary not just in space but in knowledge. At the singularity, relativity's elegant story of gravity and geometry comes to a screaming halt, leaving us with perhaps the most profound question in physics. If our best theory points to a place where reality itself becomes undefined, are we looking at the end of the universe or merely the edge of our understanding? This elegant picture of a smooth, if deadly, descent into a singularity creates a profound crisis for physics. It violates what many believe to be a fundamental law of the cosmos. According to quantum mechanics, information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. Think of it this way. If you were to burn a book, the paper turns to ash and smoke, but a hypothetical, all-knowing observer could theoretically collect every particle of soot and trace of heat, reverse the process, and reconstruct the exact words on every page. The information persists. Now take that same book and throw it into a black hole. According to Einstein's classical theory, the book crosses the event horizon, is spaghettified, crushed at the singularity, and vanishes from our universe. The information it contained, the story it told, is erased from existence. This is the heart of the black hole information paradox, a direct conflict between the two pillars of modern physics. General relativity says information is lost forever. Quantum mechanics says that is impossible. For decades, this was a disturbing but theoretical stalemate. Then Stephen Hawking made a startling discovery. He realized that black holes are not completely black. Due to weird quantum effects happening right at the edge of the event horizon, black holes can slowly leak energy. Pairs of virtual particles which constantly flicker in and out of existence everywhere in space can be torn apart at the horizon. One particle falls in while its partner escapes into space. This stolen energy comes from the black hole's own mass, causing it to very slowly evaporate. This Hawking radiation is a faint whisper of heat from the darkest objects in the universe. But it creates an even sharper version of the paradox. If a black hole evaporates completely over eons, disappearing in a final puff of radiation, what happened to all the information about every star, planet, and book it ever consumed? Did it just vanish? To rescue the law of information conservation, physicists have proposed radical ideas. One is the Firewall paradox. It suggests that instead of a smooth, empty space at the event horizon, there might be a searing wall of high-energy particles, a literal firewall that would incinerate anything trying to cross. This would preserve information by preventing anything from actually entering the black hole in the first place, but it blatantly contradicts Einstein's prediction of an uneventful crossing. Another, even more profound idea comes from theorists like Leonard Susskind. He championed the holographic principle. This mind-bending concept proposes that all the information describing the three-dimensional volume inside a black hole is not lost, but is perfectly encoded on the two-dimensional surface of its event horizon, like a cosmic hologram. The book you threw in is not gone. Its entire story is smeared and stored on the horizon's surface, one bit of information per tiny Planck area. In this view, the event horizon is not a destroyer of information, but the ultimate hard drive. This leads to a staggering possibility. If the interior of a black hole can be described by information on its surface, could the same be true for our entire universe? Are we, and everything we see, just a holographic projection from information stored on some distant two-dimensional boundary? The information paradox forces us to ask if the universe is, at its most fundamental level, not made of stuff but of data. The holographic principle suggests reality might be written on a surface, but what if that surface itself is a door? Science fiction has long dreamed of wormholes, cosmic shortcuts that fold the fabric of spacetime to connect two distant points in an instant. This is not pure fantasy. The idea is rooted in the real, if highly speculative, pages of physics. In 1935, Albert Einstein and his colleague Nathan Rosen found a surprising solution to the equations of general relativity. Their math described a structure linking the interior of a black hole to another region of spacetime, a theoretical tunnel they called a bridge. We know it today as an Einstein-Rosen bridge, the original blueprint for a wormhole. Picture the universe as a vast sheet of paper. A wormhole would be like folding that paper so 2 points touch, then piercing through with a pencil to create a shortcut tunnel. According to this early theory, the tunnel's entrance could be the event horizon of a black hole, and its exit might not be a black hole at all, but its hypothetical opposite, a white hole, spewing matter and energy out into another time or place, perhaps even another universe entirely. It is a breathtaking idea that transforms the black hole from a cosmic dead end into a potential gateway. Yet there is a formidable catch. In the standard Einstein-Rosen model, this bridge is catastrophically unstable. It would snap shut or pinch off in an infinitesimally small fraction of a second, far too quickly for even a photon of light to traverse it. The doorway slams shut almost the moment it opens. For a wormhole to be a usable passage, something would have to hold it open against this intense gravitational urge to collapse. This is where theoretical physics ventures into the truly exotic. Some solutions suggest that a form of matter with negative energy density, often called exotic matter, could provide the necessary outward pressure to prop the wormhole open. Exotic matter is not antimatter, it is something far stranger, possessing a gravitational repulsion that could, in theory, counteract the crushing weight of the tunnel walls. No such substance has ever been observed, but its possibility is hinted at in certain quantum effects. So we are left with a profound question that challenges our very image of these celestial objects. Are the black holes we observe merely the one-way tombs described by classical physics, or could they, under the right and wildly improbable conditions, be the mouths of tunnels threading through the cosmos? What if every dark silhouette against the starfield is not an end, but a handle on a door we have not yet learned how to turn? If you could play a film of a black hole in reverse, you would see its true mathematical twin. Instead of matter vanishing forever past an inescapable boundary, you would witness matter and energy erupting violently from a central point, streaming outward into space, while anything approaching from the outside is perfectly and forever reflected away. This is not a black hole. This is a white hole, a region of spacetime from which nothing can enter, only exit. It is the time-reversed mirror image of its dark counterpart, a concept that emerges naturally from the same equations of general relativity. In theory, the other end of an unstable Einstein-Rosen bridge could be such a white hole, a one-way exit into another region of our cosmos or into an entirely different universe altogether. The mathematics allows for it, painting a picture of a cosmic circuit where black holes ingest and white holes eject. Yet most physicists are deeply skeptical that white holes could exist in our stable, mature universe. The reason is entropy, the universal tendency toward disorder. A white hole spontaneously spewing out ordered energy would seem to violate this fundamental arrow of time. It would be like a shattered glass reassembling itself and leaping back onto a table. The universe as we know it appears to run in one direction, making white holes seem like improbable cosmic mirages. But what if they are not permanent structures but fleeting events? This is where a cutting-edge theory, loop quantum gravity, offers a startling possibility. This framework attempts to marry general relativity with quantum mechanics by suggesting that spacetime itself is woven from tiny, discrete loops. One of its predictions is that at the very center of a black hole, where classical physics predicts an infinitely dense singularity, quantum gravity effects create a tremendous repulsive force. Imagine a collapsing star reaching its maximum squeeze. Instead of vanishing into an infinite point, it hits this quantum wall and rebounds like a supernova in reverse. The black hole would essentially bounce, transforming into a white hole. This black hole to white hole transition would not happen quickly from an outside perspective. Due to extreme time dilation, while the bounce might be near instantaneous for the material inside, billions of years could pass for external observers. Every black hole we see in the sky today could, in this radical view, already be a white hole in its own interior frame of reference, its explosive rebirth waiting an eternity in our future. This leads to a cosmological idea of breathtaking scale. If a black hole in one universe can bounce into a white hole in another, then our own universe's explosive beginning, the Big Bang, bears a striking resemblance to a white hole eruption. Could it be that our entire cosmos, in all its splendor, is the white hole output of a gigantic black hole collapse in some parent universe? In this cyclical or multiverse picture, every black hole could be a seed for a new cosmos, a universe within a universe. Our reality, with its galaxies and stars, might then be the interior of a white hole that began some 13.8 billion years ago, while the black hole that gave it birth exists in a separate, inaccessible spacetime. This transforms the black hole from a mere destroyer of worlds into a potential creator of realities. It suggests that the boundaries of known physics may not be walls at all, but membranes between cosmic generations. All these grand visions, from wormholes to baby universes, share one immense hurdle. They require us to see beyond the point where our current physics shatters. To truly know what lies beyond an event horizon, we need a theory that does not break down at the singularity, a framework that can marry the colossal gravity of Einstein's world with the fuzzy probabilities of the quantum realm. This ultimate theory of quantum gravity remains the holy grail of modern physics, but we have two leading contenders, each painting a radically different picture of a black hole's heart. The first is string theory. In this view, the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating strings. Different vibrations correspond to different particles, like notes on a cosmic instrument. This elegant idea has profound implications for black holes. String theory suggests that the event horizon may not be the empty, smooth space of general relativity. Instead, as matter falls in, these fundamental strings get tangled and trapped at the horizon, creating a vast, chaotic ball of vibrating energy. This is the fuzzball, There is no sharp boundary, no vacuum inside, and crucially, no singularity. The black hole's entire interior is a giant, fuzzy knot of stringy matter, so dense it still traps light but finite. Information is not lost, it is scrambled and stored within this complex, vibrating structure. The fuzzball resolves the information paradox by eliminating the problematic singularity altogether, turning the black hole into a giant, exotic star made of the fabric of spacetime itself. The second contender takes a different path entirely. Loop quantum gravity does not propose extra dimensions or vibrating strings. Instead, it suggests that spacetime itself is not a smooth, continuous fabric, but is woven from tiny, discrete loops, a literal fabric of reality with a finite weave. Think of a piece of cloth. From a distance, it looks smooth and continuous, but up close you see it is made of individual threads. At the incredibly small Planck scale, a billionth of a trillionth of a trillionth of a centimeter, spacetime may have a similar granular structure. As physicist Carlo Rovelli describes it, space is not a void where things happen. It is a network of relationships, a dynamic tapestry of these quantum loops. In this framework, the crushing collapse of a star does not end in an infinite point. The granular nature of space provides a quantum bounce, a repulsive force so powerful it prevents the singularity from forming. The black hole's interior could then become a bridge, a quantum tunnel to another region of spacetime. It is not a classical wormhole held open by exotic matter, but a tunnel born from the fundamental graininess of the universe. Both theories, in their own way, attempt to erase the terrifying infinity from our equations. They replace the meaningless singularity with something highly dense, chaotic, and quantum, but ultimately finite and describable. One gives us a tangled ball of strings, the other a bridge woven from the threads of spacetime. This forces us to ask a foundational question about the nature of reality itself. Is the cosmos a smooth, continuous stage, or is it, at its very core, pixelated? Are we living in a universe of unbroken fields, or one built from countless tiny, interwoven loops? The answer, hidden beyond the event horizon, may redefine everything. We can peer across the cosmos and take a photograph of a shadow cast by nothing. In 2019, the Event Horizon Telescope collaboration unveiled the first ever image of a black hole, a fiery ring of light surrounding a dark central void at the heart of the galaxy Messier 87. This monumental achievement was not a direct snapshot of the black hole itself, which is impossible, but of its shadow, the silhouette of its event horizon against the glowing backdrop of its superheated accretion disk. That iconic orange donut is the closest we have ever come to visually confirming the existence of these cosmic boundaries, yet it is crucial to understand what we are truly seeing. The light in that image comes from matter just outside the point of no return, swirling at nearly the speed of light before it vanishes. We are seeing the last photon orbit, the final place where light can still escape. The event horizon itself lies just inside that dark central region, utterly invisible, a perfect cloak of darkness. Capturing even this shadow required a feat of staggering ingenuity. Because a black hole is so compact and so distant, observing its immediate environment demands a telescope with a resolution sharper than any single instrument on Earth could provide. The solution was to link radio observatories across the globe, from the mountains of Hawaii to the high deserts of Chile and the frozen plains of Antarctica, creating a virtual telescope the size of our entire planet. They then pointed all these dishes at Messier 87 for several nights, collecting waves of data so vast they could not be sent over the internet. The information was stored on hundreds of hard drives and physically flown to central processing centers, where supercomputers spent years combining the signals to reconstruct this single, haunting image. It is a triumph of human collaboration and technology, but it also highlights a fundamental, perhaps permanent, limit. No telescope, no matter how advanced, will ever see beyond the event horizon. The defining feature of that boundary is that it releases no information. No light, no radio waves, no particles of any kind can travel outward to tell us what is happening inside. It is the ultimate silent room. So how do we probe the mysteries of a place we can never observe? Scientists have become cosmic detectives, looking for clues in the environment just outside the darkness. By meticulously studying the behavior of the accretion disk, its flickers, its temperatures, and the powerful jets of matter it sometimes shoots out, physicists can infer properties of the black hole itself, like its spin and mass. It is akin to trying to deduce the exact shape and texture of a massive object submerged in a deep, murky pond by only studying the intricate patterns and ripples it creates on the water's surface above. Another revolutionary tool came online in 2015, gravitational wave astronomy. When two black holes spiral together and merge, they send violent ripples through the fabric of spacetime itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected these ripples for the first time, listening to the cosmic chirp of colliding darkness. The precise tone and decay of these gravitational waves carry an imprint of the event horizons that created them, allowing us to test whether they behave as Einstein predicted or show signs of the exotic physics we have been discussing. Each new tool, from planet-sized telescopes to spacetime listening posts, brings us closer to the edge, yet the interior remains shrouded, a realm for mathematics and imagination. Our theories paint vivid pictures of fuzzballs and quantum tunnels, but the event horizon stands as nature's ultimate censorship board, guarding its deepest secrets. This leaves us in a uniquely challenging position, building our understanding of the universe's most extreme phenomena not by looking directly at them, but by interpreting the whispers they leave in the world of light. To chart these invisible realms, physicists need maps that do not tear at the edges. Our standard conceptions of space and time break down completely at a black hole's boundary, so scientists employ a brilliant kind of cartography designed for infinity itself. These are Penrose diagrams named for the physicist Roger Penrose. Think of trying to draw the entire, endless surface of the Earth on a single, finite page. A standard map would have to cut off at the edges, implying the world just stops, but a clever projection, like one used for a world atlas, can wrap the globe onto a rectangular page, showing the whole thing with the north and south poles as lines across the top and bottom. A Penrose diagram does exactly this for spacetime. It uses a mathematical trick called conformal mapping to squeeze all of infinite space and eternal time into a finite diamond shape on a page. In this compressed map, the key rule is that light always travels at 45-degree angles. This simple convention lets you trace the fate of any ray of light, or any object moving slower than light with a glance. On a Penrose diagram of a black hole, the event horizon is a diagonal line that light rays approach but can never escape. The singularity is a jagged, horizontal line at the top, representing the end of time for anything inside. Most intriguingly, these diagrams often reveal symmetrical regions on the other side of the horizon, labeled as other universes or white holes, suggesting connections that our ordinary math hides. To draw such a clear map, you first have to fix a problem with the coordinates. The original Schwarzschild coordinates, which describe a simple black hole, behave badly at the event horizon. They create a mathematical singularity there, a place where numbers blow up to infinity, even though physically, nothing special happens for someone crossing it. It is like using longitude and latitude at the Earth's North Pole. All lines of longitude converge and your coordinates become meaningless, even though you are just standing on ice. To get a smooth map, physicists switch to a different coordinate system like Kruskal-Shekker's coordinates. These are the Mercator projection for black holes. Just as the Mercator map flattens the globe by stretching the poles, Kruskal-Shekker's coordinates stretch and bend spacetime mathematically to remove that false singularity at the horizon. In these coordinates, the path of an object falling through the event horizon is smooth and continuous, finally matching the physical reality that there is no sudden stop, no wall of fire, just a crossing. This mathematical toolkit is not just academic, it is the essential language for theorizing about the utterly unobservable. By using these diagrams and coordinates, physicists can rigorously explore questions that telescopes cannot answer. They can trace hypothetical paths through wormholes, calculate the behavior of quantum fields near the singularity, and model the possible bounce into a white hole. These maps do not show us what is there, but they show us all the places our equations say we could possibly go. They turn the blinding darkness of the event horizon into a structured landscape of potential, a topology of the unknown where every line and angle is a question about the fundamental nature of reality. From the particle's own perspective, crossing the event horizon is not a dramatic event at all. There is no sudden flash, no tearing sensation, no line in the sand. It is a silent, smooth passage from one region of curved spacetime to another, but this is only the beginning of its journey. Once inside, the particle is caught in an inward-flowing river of space, pulled relentlessly toward the center. The environment it enters is unlike anything known in our universe. The pressure is beyond comprehension, and the temperature soars to trillions of degrees, conditions that existed only for the briefest instant after the Big Bang. Here, the ordinary rules of matter break down completely. The dust particle, perhaps once part of a star or a distant nebula, is first torn into its constituent atoms. Then, under the colossal weight, the atoms themselves are crushed. Electrons are ripped from their orbits and forced into atomic nuclei, merging with protons to form a dense sea of neutrons. This neutron soup is what we theorize makes up the core of neutron stars, but inside a black hole, the forces are even greater. The neutrons cannot hold their structure. They too are pulverized, their components breaking down into a more fundamental state of matter. At these energies, the very protons and neutrons cease to exist as distinct entities. Instead, they melt into a swirling, superheated primordial soup known as a quark-gluon plasma. For a fleeting moment, this was the state of the entire cosmos just microseconds after its birth. In the heart of a black hole, this plasma is not fleeting. It is the new, terrible normal, but the journey does not stop there. As the density continues to increase toward the center, we enter a realm of pure speculation. Some theories suggest that even quarks, the fundamental building blocks of protons and neutrons, might not be the final level. They too could break down under such extreme conditions. In string theory, these particles would unravel into their ultimate form, vibrating loops of energy. The entire mass of the black hole could become a chaotic tangle of these strings, the fuzzball we discussed earlier. In loop quantum gravity, spacetime itself has a granular structure, a quantum foam at the tiniest possible scales. Matter approaching this scale might not be compressed into a single point, but instead be woven into the very fabric of this foamy spacetime, losing its identity as distinct particles altogether. This brings us to the ultimate theoretical limit, the Planck density. This is a number so vast it defies analogy, representing the density at which the quantum fluctuations of gravity itself become the dominant force. It is the scale where our concepts of space and time, of before and after, cease to have meaning. Crucially, this density, while unimaginably high, is still finite. It is not infinity. This provides a potential escape from the mathematical nightmare of the singularity. Matter may be compressed to this ultimate quantum scale, but perhaps it never reaches a true point of infinite density. It hits a wall of quantum repulsion, a bounce, or is transformed into something entirely new and indescribable by our current physics. So we are left with a profound question about the nature of existence itself. When matter falls into a black hole, is it ultimately destroyed, erased from the cosmic ledger? Or is it undergoing the most radical transformation possible, being broken down to its most fundamental essence and perhaps rewritten into the underlying code of reality? The journey from a speck of dust to a possible ripple in the quantum foam suggests that destruction and creation might be two sides of the same coin, a coin spinning in the darkness beyond the event horizon. The universe begins to bend around me. As my ship falls toward the stellar mass black hole, the starfield ahead does not simply brighten. It warps, pulled by the immense gravity, into a brilliant, tightening circle of blue-white light directly in front of my viewport. This is the entire cosmos, every distant galaxy and quasar, focused and blue-shifted into a searing ring of ultraviolet and beyond. It is a lighthouse beacon marking the point of no return. Behind me, the opposite occurs. The stars I am leaving behind stretch and redden, their light draining of energy, dimming into a deep crimson and then fading into an infinite blackness. I am crossing a threshold where light itself is sorted by direction, a spectral fork in the road of spacetime. From my perspective inside the capsule, the clock on my console ticks forward with a steady, reassuring rhythm. According to my instruments, the journey from the event horizon to the center will take only a matter of microseconds. This is my proper time, the unvarnished timeline of my own experience. It is finite, measurable, and terrifyingly short. I know what the physics says awaits me at the end of this countdown. The tidal forces will soon become overwhelming. The difference in gravity between my head and my feet will stretch my body into an atom-thin strand long before I reach the central point. My survival is a physical impossibility, a fact I must set aside to witness the theory unfold. Yet, as I cross that invisible boundary, I think of you, my friend, watching from the safety of a distant observation ship. From your vantage point, you are not seeing this final, swift descent. You saw me approach the event horizon, my image slowing, reddening, and freezing. To you, my clock stopped ticking at the moment I reached the edge. You will watch my final transmitted signal, perhaps a simple heartbeat ping, stretch out over the coming centuries, millennia, and eons. That single electronic pulse will be diluted into an endless, fading whisper. From your frame of reference, I will never quite cross. I become a ghost forever etched on the rim of forever, a monument to time dilation. This creates two contradictory, yet equally valid, stories of my fate. In my story, I have a conclusion. I experience a journey with a beginning, a middle, and an end, however abrupt. In your story, I have no conclusion. I am suspended in a state of perpetual, almost, a story without its final page. So which narrative is the true one? Is the reality defined by my subjective, finite experience more real than the objective, eternal image you observe? Physics insists both are correct, each within its own frame of reference. This is not a paradox of machinery, but of existence itself. It suggests that reality may not be a single, monolithic script, but a collection of irreconcilable perspectives, each complete and true for the observer living it. My final moment is both a punctuation mark and an ellipsis, depending solely on where you stand in the universe. This contradiction between my story and yours reveals a deeper principle about the universe's design. It seems reality has a built-in safety mechanism, a rule that the most extreme and unpredictable regions of spacetime must remain hidden from view. This is the essence of the cosmic censorship hypothesis proposed by the physicist Roger Penrose. In simple terms, it states that nature abhors a naked singularity, that point of infinite density where physics breaks down, is too dangerous, too lawless to be left exposed. According to this hypothesis, the universe always wraps these singularities in the protective cloak of an event horizon. forever quarantining their chaotic influence from the orderly cosmos outside. Think of it as a cosmic containment protocol. The event horizon acts as an impenetrable isolation ward, ensuring that the unknowable physics inside cannot reach out and affect the predictable, stable universe we inhabit. It is the ultimate firewall, not of energy but of unpredictability. Why is a naked singularity considered so problematic? Imagine if that point of infinite curvature, where cause and effect break down, were not hidden behind a horizon. It would be a tear in the fabric of reality visible to the outside world. From such an exposed singularity, anything could, in theory, emerge. The laws of physics as we know them could cease to apply in its vicinity. Predictability, the very foundation of science, would vanish. You could not calculate the future of anything that passed near it, as the singularity could spit out information or objects from its own unknown set of rules. It would be a source of absolute cosmic chaos, making the universe fundamentally unpredictable. For decades, cosmic censorship was widely accepted as a necessary feature of a stable, comprehensible cosmos. It was a comforting idea, a guarantee that the universe keeps its most dangerous secrets locked away. But like any good hypothesis, it has faced theoretical challenges. Researchers have explored mathematical models where, under very specific and extreme conditions, this censorship might fail. One scenario involves the collapse of certain types of exotic matter or fields that are so repulsive they prevent a full event horizon from forming before the singularity appears. Another, more persistent challenge comes from the mathematics of rotating black holes, known as Kerr black holes. These are not simple, static pits, but dynamic, spinning vortices in spacetime. Their structure is more complex, with two event horizons and an ergosphere, a region outside the outer horizon where spacetime itself is dragged around at incredible speeds. In extreme cases, if a Kerr black hole is spun up to near its maximum possible rate, the inner and outer horizons could theoretically merge and vanish. This would leave the central singularity, a ring-shaped one in this case, completely exposed, a naked ring singularity. While no known physical process is believed to naturally create such an object, the mathematical possibility forces physicists to ask a profound question. Is cosmic censorship a fundamental, unbreakable law of physics, woven into the structure of reality itself? Or is it merely a convenient assumption, a rule we hope is true because it keeps our equations sensible and our universe predictable? The answer may define the very nature of the cosmos we live in. Are we in a universe that politely hides its own incomprehensible depths, or one where, under the right circumstances, the chaotic heart of reality could one day stare back at us? The very idea of a black hole having a temperature seems to defy its own nature. How can something that absorbs all light and emits nothing possibly be described as hot or cold? Yet this is precisely the revolutionary leap that reshaped our understanding of these objects forever. A black hole is not merely a gravitational pit, it is a thermodynamic engine, governed by the same fundamental laws of heat and disorder that describe steam engines and ice cubes. This connection was first glimpsed by a young graduate student named Jacob Bekenstein in the early 1970s. He was wrestling with a troubling thought experiment. If you have a box of hot gas, it has entropy, a measure of its disorder. If you throw that box into a black hole, you have seemingly destroyed that entropy, violating the second law of thermodynamics, which states that the total entropy of the universe must always increase. Bekenstein proposed a radical fix. What if the black hole itself possesses entropy? And what if that entropy is not proportional to its volume, as it is for ordinary objects, but to the surface area of its event horizon? Each tiny fundamental unit of area on the horizon, a square of the incredibly small Planck length, could hold one single bit of information. This was a staggering idea. It meant that all the information about everything that had ever fallen into the black hole, every atom of every star, every page of every book, was not lost in the volume but meticulously encoded on its two-dimensional surface like a cosmic hologram. The three-dimensional interior was, in information terms, an illusion projected from the data on the boundary. Stephen Hawking initially resisted this idea, but his own calculations soon led him to an even more shocking conclusion. By applying quantum theory to the space just outside the event horizon, Hawking showed that black holes do indeed have a temperature. They are not absolute zero. This temperature is inversely proportional to their mass. A stellar mass black hole has a temperature of just a fraction of a degree above absolute zero, colder than the cosmic microwave background, meaning it absorbs more radiation than it emits. But a tiny, hypothetical black hole with the mass of a mountain would have a temperature in the billions of degrees, causing it to radiate energy furiously. This is Hawking radiation, the slow leak that causes black holes to evaporate over astronomical time scales. For a small black hole, this evaporation would be relatively swift and dramatic, ending in a final, theoretical pop. Now, recall the analogy of burning a book. The ashes seem like random disorder, but the information of the words is not truly gone. It is just transformed into a vastly more complicated state. Hawking's initial work suggested that when a black hole evaporates, it turns everything it consumed into a featureless thermal glow, truly erasing the information. But Bekenstein's holographic insight offered a way out. If the information is stored on the horizon's surface, then perhaps as the black hole evaporates and its horizon shrinks, that information is not destroyed but is slowly and chaotically released back into the universe through the Hawking radiation itself. The ashes, in principle, could be reassembled into the book. This transforms the event horizon from a simple boundary into the most dense hard drive imaginable, and it forges an unexpected bridge. It links the colossal gravity of Einstein's universe with the fuzzy probabilities of the quantum world, all through the universal language of information. The cosmos, in this view, might not be built first from matter and energy, but from bits and bytes written on the fabric of spacetime itself. This holographic view of reality, where information defines existence, pushes us toward an even grander possibility. What if the universe we know is not the only page in the cosmic book, but merely one chapter written by a previous one? The mathematics of black holes, when stretched to their logical extreme, suggest they could be far more than tombs or tunnels. They could be cosmic wombs. The theory of black hole cosmology proposes a breathtaking inversion. The Big Bang, that hot, dense beginning of everything we see, might not have been a singular start from nothing. Instead, it could have been the explosive rebound of matter collapsing inside a black hole in a larger, parent universe. In this view, the interior of a black hole does not end in a crushing singularity. The extreme quantum forces at its core trigger a bounce, a reversal of the collapse so violent it becomes an expansion, birthing a new space-time continuum with its own laws and dimensions, disconnected from its parent. Our entire cosmos, with all its galaxies and stars, could be the vast, expanding interior of a white hole that began 13.8 billion years ago. This idea finds a fascinating echo in the work of physicist Lee Smolin, who proposed a theory of cosmological natural selection. He suggested that if new universes are born inside black holes, they could inherit, with slight random variations, the fundamental constants of their parent universe. Universes that are better at producing black holes would, in this cosmic evolutionary tree, have more offspring. Over countless generations, this would naturally select for universes, like our own, that are finely tuned to create the very conditions necessary for black holes to form, and by extension for stars, planets, and life to arise. It is a staggering thought, The laws of physics we measure, the strength of gravity, the mass of an electron, might not be fundamental truths written in stone, but the result of a long line of cosmic ancestry shaped by a simple reproductive rule. This stands in contrast to another powerful multiverse idea, the inflationary model. Here, our universe is one bubble in a frothing, eternal sea of false vacuum energy. New bubble universes constantly nucleate in this greater cosmos, each with its own random set of physical laws, forever out of reach from one another. In this picture, black holes might not create new universes, but could serve as tenuous bridges, wormholes, connecting these otherwise isolated bubbles. Both frameworks, though different in mechanism, point toward a reality of unimaginable plurality. They transform the black hole from a destructive end into a potential source of cosmic fecundity, a generator of diversity in the laws of nature themselves. This leads us to a question that redefines our place in existence. Are we, and everything we hold as the totality of reality, simply the aftermath of a stellar collapse that occurred in a higher dimensional space we can never perceive? Are we living inside the echo of a distant cosmic event? The simple, static black hole is a powerful thought experiment, but it is not the reality of our cosmos. Most real black holes are likely born from the collapse of spinning stars, and that angular momentum is conserved, creating a whirlpool in the fabric of spacetime. These are described by the Kerr solution, a more complex and dynamic map of reality. Around a rotating black hole, something extraordinary happens. Outside the event horizon, there exists a region called the Ergosphere, an oblate, pumpkin-shaped zone where spacetime itself is dragged around by the black hole's spin. Imagine standing in a powerful river current. Even if you are not being pulled directly downstream, the water rushing past you makes it incredibly difficult to stand still or move against the flow. In the Ergosphere, spacetime is that river. It is moving so fast that nothing, not even light, can remain stationary. You are forced to move in the direction of the rotation, caught in a cosmic whirlpool. This leads to a mind-bending possibility for energy extraction, known as the Penrose process. Imagine an advanced civilization sending a probe into the Ergosphere. The probe splits into two pieces. One piece is sent on a trajectory that falls into the black hole, while the other is programmed to escape. If the maneuver is precise, the piece that falls in is given a negative energy orbit relative to the distant universe. To conserve energy, the piece that escapes emerges with more energy than the original probe had. The black hole itself pays the bill, losing a tiny amount of its rotational energy and slowing down slightly. It is a direct mining of a black hole spin, a concept that sounds like pure science fiction but is grounded in solid general relativity. The interior of a Kerr black hole is even more bizarre than its energetic exterior. Instead of a single point-like singularity, the equations suggest a ring singularity, a loop of infinite density. And there is not just one event horizon, but two, an outer and an inner horizon. Between them lies a region of potentially normal spacetime. Some theories speculate that passing through the inner horizon might not lead to a crushing end, but could serve as a gateway to other universes or other parts of our own. Of course, most models suggest the inner horizon is violently unstable, a place where infinite energy from the future piles up, making it more of a theoretical curiosity than a practical portal. Still, the Kerr model reveals a crucial truth. The classic Schwarzschild black hole is just the introductory chapter. Real black holes are not simple pits. They are dynamic, spinning engines, capable of storing immense energy in the very fabric of moving space around them. They are less like a still well and more like a galactic maelstrom, where the water itself is the structure of reality. This holographic vision of black holes is not just a clever trick for storing data. It points toward a principle that could redefine the very nature of reality itself. The holographic principle is a radical proposal born from the thermodynamics of black holes. It suggests that all the information needed to describe everything within a three-dimensional volume of space, every star, every atom, every event, can be perfectly encoded on the two-dimensional boundaries surrounding that volume. Think of a hologram on your credit card. The flat, shiny surface contains all the data necessary to project a three-dimensional image that seems to have depth and solidity. In this view, our rich, three-dimensional universe, with all its galaxies and swirling nebulae, might be a magnificent projection from information stored on a distant, two-dimensional surface we cannot see. This idea found its most precise mathematical form in the work of physicist Juan Maldacena. In the late 1990s, he discovered a stunning correspondence, now called the AD-SCFT correspondence. It proved, within a specific theoretical model, that a universe with gravity in its interior is completely equivalent to a quantum field theory without gravity living on its boundary. It is a dictionary translating between two seemingly different worlds. One page describes a volume of spacetime with black holes and gravitational forces. The other page describes a flat, lower-dimensional world of quantum particles. Both descriptions are different translations of the same fundamental information. This has profound implications for what lies beyond an event horizon. If the holographic principle holds, then the interior of a black hole, that mysterious volume of warped spacetime and potential singularities, is not a separate physical place in the traditional sense. It is an encoded representation, a three-dimensional image projected from the quantum data dancing on the event horizon's two-dimensional surface. The journey of an astronaut falling in would be, from this perspective, the translation of their information from one form into another, like a story being rewritten in a different language on the horizon's skin. The paradox of what happens to them inside becomes a question of how information is processed and stored, not a question of traveling to a hidden location. This leads to a staggering possibility about the cosmos we inhabit. Could our entire universe, with its billions of galaxies stretching across vast distances, be the holographic projection from a flat, two-dimensional shell at the edge of everything? Is the depth we experience, the space between stars, an emergent illusion built from countless quantum bits of information interacting on a surface we will never perceive? If true, it means the universe is fundamentally simpler than it appears. The deepest laws of nature may not be written in the language of three-dimensional space and time, but in the language of information transfer and quantum entanglement on a lower-dimensional canvas. We are left wondering if the ultimate boundary of known physics is not a horizon in space, but a limit of perception where the solid world we know dissolves into a shimmering pattern of data. But to truly grasp how a black hole evaporates, we must shrink our perspective to the very edge of reality. At the quantum scale, right at the lip of the event horizon, the vacuum of space is not an empty void. It is a seething, frothing sea of potential. Here, the rules allow for a fleeting miracle. Pairs of particles and their antimatter opposites, known as virtual particles, constantly wink into existence, borrowing energy from the quantum field for an imperceptibly short moment before annihilating each other and returning the energy, a dance of creation and destruction happening everywhere all the time. Normally, this dance is perfectly balanced with no net effect, but place this quantum froth at the precipice of a black hole and the balance is shattered. Imagine one of these virtual pairs appearing right at the boundary. In the violent tidal forces of the spacetime curvature, the two particles can be torn apart before they can reunite. One particle falls across the event horizon into the black hole. Its partner, however, is flung outward, escaping into the universe as real radiation. This is the heart of Hawking radiation. From the outside, it appears the black hole is glowing with a faint heat, but there is a cosmic cost. To preserve energy conservation, the particle that fell in must have negative energy relative to the distant universe. This negative energy reduces the total mass and therefore the total energy of the black hole itself. Over timescales longer than the age of our universe for a stellar black hole, this slow quantum leak causes the black hole to lose mass, shrink, and eventually, in theory, evaporate completely. It is a stunning connection between the quantum weirdness of the very small and the gravitational might of the very large. Yet this elegant picture runs into a profound puzzle called the trans-Planckian problem. If we trace the path of the escaped Hawking particle backward in time to its origin point extremely close to the horizon, we find it would have needed to have an impossibly high trans-Planckian frequency. It would have carried more energy than is theoretically possible in our current understanding of physics, a wavelength shorter than the Planck length, the scale where spacetime itself may become granular. This suggests our smooth description of spacetime as a continuous fabric breaks down much earlier than we thought, hinting that a theory of quantum gravity is essential to fully describe even the first whisper of a black hole's evaporation. This quantum activity at the horizon finds a cousin in another strange effect, the Unruh effect. An observer floating in empty space sees a vacuum, but an observer accelerating relentlessly, like someone in a constantly firing rocket ship, would not see a vacuum. They would perceive themselves as being bathed in a warm glow of particles, a thermal bath created purely by their own motion. The accelerating observer's frame of reference splits the quantum field in a way that creates real particles where an inertial observer sees none. The event horizon, with its intense gravitational acceleration, creates a similar splitting, so we can visualize Hawking radiation not just as stolen particles, but as the black hole's own version of the Unruh effect, a thermal glow intrinsic to its fierce gravitational field. Picture a pot of water on the verge of boiling. Tiny bubbles of steam form at the bottom, detach, and rise to the surface. The Hawking radiation process is analogous. The quantum vacuum near the horizon is like that heated water, bubbling with virtual pairs. The black hole's gravity is the heat tearing the bubbles apart. The escaped particles are the steam carrying energy away into the cosmos. This micro-scale quantum turmoil, this endless bubbling at the boundary, is the hidden engine driving the black hole's macro-scale fate. It ties the ultimate destiny of these cosmic giants to the fleeting dance of the smallest things in existence. A grand piano, a cloud of hydrogen, and a dying star all share the same potential fate. If you were to watch each one vanish past the event horizon of a black hole, could you ever tell what had fallen in? According to one of the most elegant and troubling ideas in theoretical physics, the answer is no. This is the essence of the no-hair theorem. It states that a black hole, once it has settled into equilibrium, can be completely described by just three numbers: its mass, its electric charge, and its spin, or angular momentum. Every other detail, every unique characteristic of the matter that formed it or later fell in, is irretrievably erased. This lost information is poetically called the hair, and the theorem says black holes have none. They are the ultimate bald objects in the cosmos. Think of it like a cosmic blender of unimaginable power. You can put in a strawberry, a banana, and a handful of spinach. Each is distinct with its own color, texture, and nutritional story. But once you press the button, those identities are gone. You are left with a smooth, green liquid. From the smoothie alone, you cannot reconstruct the original strawberry. The black hole, in this view, is that blender. It takes the complex, ordered information of a star or a spaceship and turns it into a featureless, three-ingredient recipe. This presents a deep puzzle about identity in the universe. If all distinguishing features are lost, then a black hole made from a collapsed star is fundamentally identical to a black hole of the same mass, charge, and spin made from a collection of grand pianos. The cosmos, it seems, possesses a terrifying efficiency for getting the specifics of what it consumes, yet this clean picture is now facing serious challenges. When the LIGO Observatory first heard the chirp of colliding black holes, it did more than confirm their existence. It provided an exquisitely detailed fingerprint of the event, a ripple pattern that encodes the properties of the black holes before they merge. Scientists are now meticulously analyzing these gravitational wave signals, searching for tiny deviations, subtle echoes or aftertones that might betray hidden structure, a faint memory imprinted on the horizon itself. This search is driven by groundbreaking theoretical work, notably from physicists like Stephen Hawking, Malcolm Perry, and Andrew Strominger. They proposed that black holes might, in fact, have soft hair. This is not hair in the traditional sense, but an infinite collection of zero-energy excitations, like infinitesimally gentle ripples on the surface of the event horizon. These ripples would be caused by the gravitational pull of every single particle that ever crossed the boundary. While each imprint carries virtually no energy, together they could, in principle, store a vast amount of information about the black hole's history. It would be like the smoothie retaining a quantum-level memory of every cell in every fruit, not in their original form, but in a ghostly, holographic code. The debate between the classic no-hair theorem and the new soft hair hypothesis cuts to the very heart of the information paradox. Is the universe a place that ultimately forgets, smoothing all complexity into simple, forgettable forms? Or is it a meticulous archivist, preserving every detail in a language we are only beginning to decipher, written in the faintest of whispers on the boundary between light and darkness? Gravity's final act is a silent one, but we have learned to make it sing. The faint chirp heard by LIGO did not emerge from a simple calculation on a chalkboard. It was born in the heart of a supercomputer from a field of science called numerical relativity. Here, physicists do not just solve Einstein's equations. They set them in motion, translating the abstract geometry of curved spacetime into billions of lines of computer code. They create virtual universes inside machines, where they can choreograph the collision of two black holes with pinpoint precision, watching as their event horizons stretch, merge, and settle into a single, quivering new dark heart. These simulations are our wind tunnels for the cosmos. We cannot fly a plane into a black hole, but we can build a perfect digital model of one and crash it again and again to see what happens. The output is more than a pretty visualization. It is a precise prediction of the gravitational wave signal such a collision would produce, a template that allowed LIGO to recognize the real thing amidst the noise of our planet. By comparing the simulation's chirp to the one detected from deep space, scientists perform the ultimate test of general relativity in its most extreme regime. Every ripple, every frequency shift in the simulated signal tells a story about the stability of the event horizons during the violent merger, and how the final, larger black hole rings down, vibrating like a struck bell before going silent. This is how we experiment with the unexperimentable, probing the dynamics right at the edge of forever from the safety of a server room. Yet even our most powerful simulations face a formidable wall. They excel at modeling the classical dance of spacetime described by Einstein, but they cannot yet penetrate the quantum chaos believed to reign at the central singularity. The scales are too different, the physics too unknown. Simulating the moment where a singularity might form, or where quantum gravity effects take over, is like trying to model the precise behavior of every molecule in a hurricane. Our computers and our theories are not yet up to the task, so for now, the very core remains a blank spot in the simulation, a question mark hidden behind the profound certainty of the event horizon's evolution. We have mapped the gravitational storm with stunning accuracy, but the eye of that storm remains a mystery, waiting for a new generation of code to illuminate the darkness. Our most powerful simulations crash against a wall of pure theory. We can chart the gravity, but not the grammar of what lies at the center. This confrontation forces a humbling realization, one that transcends physics and touches the very nature of our quest. The black hole presents us with something more profound than a physical boundary. It may be an epistemological boundary, a limit not merely of what we can see, but of what we can possibly know from our position in the cosmos. We are like sailors mapping an island from a distant shore. We can chart its coastline with incredible precision, measure the tides that lap its beaches, and infer the mountains within from the shadows they cast. But the dense jungle at its heart, the true interior, remains inaccessible to our tools and perhaps even to our concepts. The event horizon is that final shoreline, and what lies beyond may be terra incognita in the most absolute sense. The philosopher of science Thomas Kuhn taught us that scientific understanding does not progress in a smooth, steady line. It advances through revolutions, what he called paradigm shifts, where an old framework for understanding the world shatters under the weight of its own contradictions, and a new, incommensurable one takes its place. The world before and after such a shift can look fundamentally different. The crisis posed by the black hole singularity, the paradox of information, the clash between quantum and gravitational laws, all point to our current paradigm straining at its seams. The physics needed to describe what is beyond the horizon may not be a simple extension of our current equations. It may require a conceptual revolution so profound we cannot yet imagine its shape, a new way of seeing reality that would make our current questions seem quaint. This leads to a haunting possibility. Are some truths about the universe simply not accessible to minds like ours, shaped by evolution in a gentle, middle world of trees and tides? Is the interior of a black hole, or the origin of the cosmos, fundamentally unknowable, not because of technological lack, but because of a cosmic censorship of understanding itself? This is not a call to surrender curiosity, but to refine its nature. Does the existence of such an ultimate boundary humble our scientific ambition, or does it in fact inspire it? The very act of confronting the unanswerable, of mapping the shoreline of ignorance, is a profound human achievement. It tells us where the map ends and the mystery begins. Our drive to ask the questions we may never fully answer is what transforms us from passive inhabitants of the cosmos into active participants in its story. The black hole, in its perfect darkness, holds up a mirror. It reflects back to us not just light, but the luminous and limits of our own relentless wonder. Perhaps our entire approach to gravity has been wrong. For decades, the dominant story of the cosmos has rested on two invisible pillars, dark matter and dark energy. We infer their existence because galaxies rotate too fast and the universe expands too quickly for the visible matter alone to explain. But what if the problem is not with the contents of the universe, but with the rulebook itself? A bold school of thought suggests we do not need dark ingredients. Instead, we should rewrite the law of gravity on cosmic scales. This idea is known as modified Newtonian dynamics, or MN. At its heart, MN proposes a simple but radical change. In regions of extremely weak gravity, like the outer fringes of galaxies, the force of gravity stops following Newton's familiar inverse square law and becomes stronger. This extra gravitational kick could explain why stars on the edges of galaxies whip around so fast without needing the gravitational glue of unseen dark matter. It is a compellingly simple fix, but it faces a monumental challenge. MN, in its original form, was a modification to Newton's old laws, not to Einstein's more complete theory of gravity, general relativity. To be a true contender, it needed a relativistic upgrade, a way to explain not just galaxy rotations but also gravitational lensing and the expansion of the universe. Several theories now attempt this with names like TVS or tensor vector scalar gravity. These frameworks create a new playing field, and in doing so, they inevitably change the rules for the most extreme players of all, black holes. In some modified gravity theories, the predictions about event horizons and singularities shift dramatically. The mathematical point of infinite density might be avoided altogether. Instead, the collapse of a star could halt, not by neutron degeneracy pressure, but by the new rules of the modified gravitational force itself. This opens the door to hypothetical objects that look like black holes from afar, but are fundamentally different beasts at their core. Enter the gravistar, short for gravitational vacuum star. Imagine a star so dense that its core is not a soup of neutrons or a singularity, but a bubble of pure dark energy, the same repulsive force accelerating the universe's expansion. This bubble would be surrounded by a shell of ultra-dense, exotic matter. Crucially, a gravistar would have no singularity and no true event horizon. There would be a surface, and matter could, in theory, accumulate on it, but the gravity would be so intense that light would be severely bent and redshifted, creating a dark shadow almost indistinguishable from a black hole's. Another speculative object is the dark energy star, a similar concept where the interior is a region of repulsive dark energy, preventing total collapse. If such objects exist, they would mimic a black hole's appetite and its shadow, but would lack the one-way door of an event horizon. The information paradox would vanish, as nothing ever crosses a point of no return. So how could we ever tell the difference between a classic black hole and one of these exotic imposters? It comes down to exquisite forensic observation. The Event Horizon Telescope image of Messier 87 was a first fingerprint. Future, sharper images and more detailed studies of the black hole shadow could reveal subtle signatures. For instance, the shadow of a true black hole should be almost perfectly circular if the black hole is not spinning much, and become more flattened or skewed if it is. The precise shape and size of that shadow depend intimately on the spacetime geometry right at the event horizon. A gravistar or dark energy star, with its different internal structure and lack of a true horizon, could cast a shadow with a slightly different profile, perhaps with a faint, glimmering ring structure where light from its surface manages to escape. It is like diagnosing an illness where two different conditions produce nearly identical symptoms. A doctor relies on tiny, telltale clues in the bloodwork or a nuanced reaction to a test. For astronomers, the bloodwork is light, and the test is the extreme environment just outside the darkness. By studying the precise way matter flickers and falls, the exact silhouette of the shadow, and the behavior of stars orbiting perilously close, we may one day see a signature that does not fit Einstein's pristine prediction. That single anomaly could force a revolution, proving that the darkness we see is not a hole in space-time, but something even stranger, a star built from the universe's own accelerating breath. Our existence might be a clue written into the fabric of the cosmos. This is the essence of the Anthropic Principle, a simple yet profound line of reasoning. It suggests that the universe we observe must have the properties it does because if it were even slightly different, we would not be here to observe it. We are not passive witnesses to a random cosmos, but active participants in a universe capable of generating conscious life. When we apply this lens to black holes, a fascinating connection emerges. These cosmic engines are not just destructive oddities, they appear to be finely tuned components in the architecture of a life-friendly universe. Consider the delicate balance required for a galaxy like our Milky Way to form and persist. At its heart sits a supermassive black hole, Sagittarius A star. Its immense gravity helps shape the galactic core, but it is not so voracious that it devours the entire galaxy. Its activity through jets and energy output may even regulate star formation. Now, imagine a counterfactual universe where the laws of physics made black holes far too easy to create. In such a cosmos, every large star might collapse directly into a black hole, seeding space with countless dark traps. Galaxies would be shredded from within, their stars swallowed before planetary systems could even coalesce. Stable, long-lived solar systems like our own would be impossible. Conversely, picture a universe where black holes were impossible to form. Without the gravitational anchors of supermassive black holes, galactic centers might never condense. The violent mergers of galaxies, which trigger new waves of star formation and scatter heavy elements essential for planets and life, might play out very differently. The cosmic recycling of matter would follow an unknown script, one that may not lead to rocky worlds or stable suns. The very parameters that govern gravity and nuclear physics, the strength of the forces that dictate how stars live and die, seem calibrated within a narrow window. This window allows for the existence of black holes, but also for the vast, quiet stretches of galactic real estate where life can arise undisturbed. This leads us back to the speculative ideas of universe generation. If black holes are seeds for new cosmos in a multiverse, then the laws within each new universe could be slightly different, a random variation from its parent. In this grand cosmic Darwinism, universes that produce black holes efficiently have more offspring. Our universe, with its specific constants, is one that abundantly creates black holes. And not coincidentally, those same constants also allow for chemistry, for water, for DNA, for observers. So when we peer into the abyss of an event horizon, we might be looking at more than a mystery. We could be staring at a necessary condition for our own reality. The same physics that creates the darkness also carves out the safe harbors where light and life can flourish. This intertwining of life and cosmic violence poses a humbling, reflective question. Is our curiosity about what lies beyond the event horizon, in some deep sense, the universe's way of trying to understand its own reflection? The quest to understand the darkness is building new eyes and ears for humanity. While the Event Horizon Telescope gave us sight and LIGO granted us hearing, the next generation of observatories will give us a deeper, more resonant sense of the cosmos. Enter the Laser Interferometer Space Antenna, or LISA. This is not a single telescope, but a constellation of 3 spacecraft, flying in a perfect triangular formation millions of miles apart, connected by laser beams. By precisely measuring the distance between these free-floating cubes, LISA will listen for the low-frequency hum of the universe, a gravitational wave chorus that ground-based detectors like LIGO cannot hear. Its prime target will be the mergers of supermassive black holes, events so colossal they send ripples through spacetime for millions of years. By tuning into these deep cosmic notes, LISA will map the dance of darkness on the very largest scales, telling us how these behemoths spin, how they warp spacetime around them, and perhaps even revealing the unique ring-down of the final, merged event horizon. It is like developing a sense of echolocation for the cosmos, using the echoes of titanic collisions to paint a picture of objects we can never see directly. But some scientists are not waiting for cosmic events. They are building black holes right here on Earth. Of course, they are not creating true gravitational pits, but ingenious analogs. By using carefully controlled materials like super-cold fluids or specially structured glass, researchers can trap pulses of light or sound waves in a way that mimics an event horizon. In these lab-made analogs, something remarkable happens. Just as light cannot escape a real black hole, sound or light waves in these materials can be trapped, creating an artificial point of no return. And just as Stephen Hawking predicted, these analog horizons can produce a faint thermal glow of particles, a simulated version of Hawking radiation. By studying these controllable systems, physicists hope to unlock the quantum secrets of real event horizons, testing theories about information and radiation in a tabletop experiment. It is a brilliant workaround, a model of the cosmos built from lasers and superfluid helium. Looking even further ahead, the probes we send may not be made of metal and circuitry, but of quantum information itself. Some theorists speculate about sending a simple, unmanned quantum probe, a packet of carefully entangled particles, toward a black hole. The goal would not be to retrieve the probe, but to study how its quantum state, its most fundamental information, is scrambled or preserved as it interacts with the horizon. It would be the ultimate test of the holographic principle, a message in a bottle thrown into a cosmic ocean to see if the bottle shatters or if its message is merely translated onto the surface of the waves. While this remains a distant theoretical dream, it underscores a profound shift in thinking. We are moving from simply observing black holes to interrogating them, from passive astronomy to active cosmic experimentation. Each of these ventures, from space-based laser arrays to quantum messages, represents more than just new technology. They are the embodiment of a human impulse to reach beyond the boundary of the knowable. We are building new senses for our species, not with biology, but with mathematics and engineering. The event horizon stands as the ultimate silent wall, but we are learning to listen to the vibrations it sends through the very framework of reality, and to read the subtle codes it may imprint on the quantum world. The darkness may not give up its secrets easily, but our resolve to illuminate it has never been stronger, driving innovation at the very edge of what is possible. The human mind has always drawn maps for the places it cannot go. Long before we plotted the Schwarzschild radius, our ancestors told stories of thresholds that could not be uncrossed. The river Styx of Greek myth was not just a body of water, it was a boundary between the worlds of the living and the dead, a one-way passage where the ferryman demanded his fare. The Norse Bifrost Bridge was a shimmering, fiery pathway to Asgard, a connection between realms that would shatter at the final battle. These were mythological event horizons, points of no return that separated the known from the unknowable, the mortal from the divine. In every culture, the abyss took a shape, and crossing it meant a fundamental transformation, a loss of the old self. Today, the black hole has become that archetype for our scientific age. It is our modern river Styx, our cosmic Bifrost, a physical manifestation of the ultimate unknown that has always waited at the edge of our stories. It is no accident that in film and literature, from the terrifying monolith in 2001, A Space Odyssey, to the navigable wormhole in Interstellar, the black hole serves as both a plot device and a profound symbol. It represents existential fear, the terror of being erased without a trace. Yet it also symbolizes radical transformation, a gateway to another state of being, another universe, or a deeper understanding. Artists paint its darkness, musicians score its dissonant beauty, and philosophers wrestle with its implications. The poet Rainer Maria Rilke once wrote of gazing into the terrifying, for in that gaze we also find beauty. The black hole is our collective terrifying, a mirror held up to our deepest questions about oblivion and infinity. When scientists like Subramanian Chandrasekhar calculated the fate of collapsing stars, or when Roger Penrose diagrammed the paths of trapped light, they were engaged in an act as old as humanity, drawing a better map of the abyss. This contextualizes our entire scientific pursuit. The drive to understand what happens beyond an event horizon is not a cold, detached calculation. It is the latest chapter in the long human tradition of confronting the void and asking what it means for our existence. We code simulations and launch telescopes for the same reason ancient poets sang of underworld journeys, to find meaning at the boundary. Our equations are our epic poems, and the singularity is our modern dragon, guarding a treasure we cannot yet name. This connection between myth and mathematics reminds us that curiosity about the darkness is not merely a function of intellect, but of spirit. We are drawn to the event horizon because it is the final, silent answer to the question every culture has asked in its own language: what lies beyond the last light? The landscape of modern physics is not a single path to truth, but a vibrant, contested frontier. After this long journey through equations and imagination, where does the scientific community currently stand on the question of what lies beyond an event horizon? There is no unanimous verdict, but there is a powerful consensus on one critical point. Most physicists agree that the classical singularity predicted by general relativity, a point of infinite density, is not a physical reality. It is a glaring sign that Einstein's magnificent theory, so successful everywhere else, has reached its breaking point in the heart of a black hole. To move past this mathematical crisis, we require a deeper framework, a theory of quantum gravity that can describe the universe where it is both incredibly tiny and unimaginably dense. The two leading contenders for this ultimate theory, string theory and loop quantum gravity, offer radically different visions of what replaces that dreaded singularity. In one, the black hole's interior becomes a tangled fuzzball of vibrating strings, a finite yet impenetrable quantum knot. In the other, the granular structure of spacetime itself provides a quantum bounce, potentially creating bridges to other realms. Both are mathematically elegant, intellectually profound, and remain, for now, beyond the reach of direct experimental proof. They are maps drawn in different languages, each claiming to chart the same unknown territory. Amidst these competing visions, one puzzle stands as the central, unsolved, not tying all the threads together: the black hole information paradox. This is the stubborn conflict between the smooth spacetime of general relativity and the unbreakable rules of quantum mechanics. It asks whether information that falls into a black hole is truly lost forever, erasing a fundamental law of the cosmos, or if it is somehow preserved, scrambled on the horizon, or encoded in Hawking radiation. Resolving this paradox is not just about black holes. It is about determining whether our universe is ultimately predictable and unitary, or if true randomness and erasure can occur at its most extreme edges. So, what is the answer for science today? The answer is not a statement, but a spectrum of breathtaking possibilities. It is the entire conversation we have just had, from the destructive singularity to the creative white hole, from the holographic principle to the cosmic sensor. Each idea is a legitimate, rigorously explored hypothesis on the scientific frontier. This lack of a single, neat conclusion is not a failure of science, but a testament to its vitality. It means we are actively living in a moment of profound questioning, where the most fundamental nature of reality is being debated not in philosophy halls, but through mathematics and observation. The journey to the edge of knowledge does not end with a simple revelation. It opens into a wider, more mysterious landscape of what might be true. We have traced the line where physics ends and philosophy begins. From the stark certainty of a crushing singularity to the shimmering possibility of a holographic universe, every theory we have explored is a testament to human imagination confronting the absolute unknown. The event horizon is more than a boundary in space. It is a mirror reflecting the limits of our current knowledge, a silent challenge written into the fabric of reality itself. Its true power lies not in the answers it provides, but in the profound questions it compels us to ask. What is the fundamental nature of information? Does time have a true direction? Is our three-dimensional world an illusion projected from a deeper, simpler truth? Each time we point a telescope toward that darkness or run a new simulation, we are not just studying a distant object. We are stress-testing the very framework we use to comprehend existence. This journey to the edge reveals that the universe is far stranger and more wonderful than we ever supposed, holding mysteries that reshape our place within it. Let this exploration be a starting point for your own curiosity. Which vision of the ultimate interior speaks to you? Do you see a gateway, a fuzzball, or a cosmic cradle? Share your thoughts in the comments below, and if you want to continue exploring the edges of knowledge, subscribe to join us for the next mystery waiting in the dark.